All right. Good morning, everybody. How are you doing? Are you awake? Who has a coffee in the morning before you come to class? Not so many. Okay. All right. You know, I actually don't drink coffee, even though I'm from Colombia. So my theory is that my body makes its own caffeine, so I don't need to drink it. Yeah. Anyway, so today we're gonna finally talk about derivatives. This has all been preparation. Yes, right? We should cheer. Do you guys know who invented derivatives? Do you guys know Isaac Newton? Okay. What else did he invent? Okay. And what else?
Invented the concept of the laws of gravity.
Laws of gravity, that's right. He's the guy who figured out how, why the moon goes around the Earth. Back then it was almost like a philosophical question that had no answer. Just the moon goes around the Earth, that's it. And he actually figured it out. And he also invented calculus. You guys know the story with the apple, right? So he must have hit so hard, that not only did he invent gravity laws, but also calculus. Actually, there was a big discussion back in the 1600s because another guy, a German, called Leibniz, he also pretty much invented it independently, but Newton had told him something, and so it wasn't clear if he really invented it or not. There's a big discussion, lots of lawsuits back in that time, made everybody bitter about it, and basically it ended up being so that in Europe, people followed Leibniz for many years, and in England, people followed Newton's. So there was basically, it split the mathematical community into two groups. Anyway, I'm getting too much ahead of myself. Well, I'm not really going to tell you more about it much later, but there's a lot of politics in math. Who would have thought, right? Anyway, so today we're going to talk about derivatives, and we're going to be using all these ideas we learned so far, like limits and so on and so forth, and we're going to put them to good use in this context. So the question we were talking about last time, and now we can answer it, is how do we measure or how do we compute the slope of a tangent line. Right? If you remember, last time we had said that we didn't really have the tools to answer that question. It's actually a hard question, and I'm going to remind you what the framework for this question is. Basically, you have a function, f of x, and you have a point A, and you have the tangent line. Let's say tangent line looks more or less like this. You can see it in the graph. There's no problem with seeing it. The problem is actually computing what the tangent line's slope is. So we had this idea. Actually, one of you suggested this idea, which I thought was very good. And that idea was to take a point nearby and to draw a line from this point to this point and to calculate the slope of that. Okay? What was the slope of that? That's the approximate slope. Approximate slope and I want you all guys to understand this graph because it basically has all the information you need. How do you calculate the slope? Well, the slope is computed by taking this triangle and calculating the rise and the run. What is the length of that run, the horizontal line? What do you think?
X minus A.
X minus A, that's right. Okay, what about the rise? How high is that line? How tall is that line? F of x minus f of A, that's right. So I want you all guys to agree on this. The height that goes all the way from down here to up here is f of x, right? All the way up to here. The height all the way up to here is f of a. So this distance from here to here is the difference between those two, f of x minus f of a. Great. So the approximate slope is roughly f of x minus f of a divided by x minus a. You agree? Awesome. So now that we know much more than we did a week or two ago, how do we calculate the exact slope? Well, if you remember, we said this is not the actual slope. You can see the dotted line and the solid line are not the same. We can make it better by taking a point x that is closer to a, right? We cannot really set x equal to a because then the bottom thing is equal to 0. But we can make x very, 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 very close to a. And the closer we make it to a, the closer the answer. The closer that the approximate slope becomes to the actual slope. So, as we take points that are, let me draw a again, and the actual tangent line. As we take points that are closer and closer to a, for example, this point right here, I'm going to get closer and closer values to the actual tangent line. Okay? And the actual tangent line has slope. The actual slope is m equal to the limit, right? So this is really the punchline, is that you have to take the limit as x approaches a of that approximate slope. The limit of f of x minus f of a divided by x minus a as x approaches a. That is really it. That is really the way to calculate slope. Now, the slope of a function obviously depends on where you draw the tangent line, right? It depends on the point where you're standing. So I'm going to write this down. Of course, the slope depends on the point A okay, and we're going to use this idea of the slope as a definition of the derivative. So the derivative of a function f at the point A is the slope of the function f at, of the tangent of, the tangent of f at A. So that is, mathematically, we define f prime of A. This is going to be the name of the derivative. F prime is going to be defined as the limit when x goes to A of f of x minus f of A divided by x minus A. So let me say this again in words. You got a function. You're given a function f of x with some formula. You draw it, okay? And you look at any point A. At any point A, you can draw the tangent, calculate the slope, and you call that f prime of A. So f prime is going to be a function of its own. Okay? It's a funny function. It's a function that in comes the point A, and out comes the result of drawing the line, drawing the tangent, and calculating the slope. Okay? So f prime of A is the slope of f at the point A. We're going to follow our standard procedure of first doing a graphical example, which I think is easier, and then we can start talking about the algebra.
Quickly,
Yes, question?
we want to find out the derivative of A, right? Not of X?
The derivative of the function f at the point A, not at x.
Right.
That's right. Yeah, later, that's a good question. What about, why do I call it f prime of A and not f prime of x? Well, basically I'm looking at a particular point A. I'm doing all these graphs and all these drawings around A. So this is really f prime of A. Okay. Later on, we're going to be a little bit more, little bit less precise with the notation, if you will. But for now, we're going to think about a particular point A, and we're going to calculate the slope at that point. So let me give you a graphical example. Of what I mean. And I'm going to consider a function. I'm going to cheat a little bit. I'm going to start by drawing the tangents, just so I can draw the function later. So here's the tangent, and here's the function. Let's say at the point 4, we have a horizontal tangent. So it looks like this. At this point 6, I have a tangent more or less like this. And at, let's say, this point, I have much more vertical tangent line. So let's see. So the tangent line looks here like this, here, and here. Great. Okay, so here's my function f of x. And I calculated the tangent line at a bunch of points. So the tangent line over here represents the tangent line at 2. So what can we say about the function f prime at 2? Let's see, f prime of 2 is equal to what? Who can tell me? The slope of the function, the slope of the tangent of the function at the point 1, which is more or less what?
Tangent.
Yeah, but what's the number, more or less? What's the slope of a function that looks like this, of a line that looks like this? More or less positive 1, that's right. Okay? So you draw, I mean, I'm not going to do it, but you can draw this triangle, you can calculate the rise over the run, and then roughly speaking, f prime of 2 is 1. Okay. Now, the function has a horizontal tangent at f equals 4. So what does that say about the function f prime? 0, right? Exactly. So f prime of 4 equals 0 means, by definition, right, this derivative at the point A is the slope of the tangent of f at the point A. So basically, the function has a horizontal tangent, so the slope of this line is 0, and f prime of 4 is 0. What about f prime of 6? Well, first of all, it's negative because the tangent is pointing in a different direction, and it's pretty steep, so it's more than not just -1, but it's more or less like -2, something like that, right? Okay, something like -2. By that I mean that if I drew a triangle here, basically this distance will be twice as much as the horizontal distance. And because it's pointing this way, not this way, it's -2 instead of +2. Okay, and what about f prime of 10?
Positive
4.
3.
Positive 4, yeah, something like that. 4, maybe 5, something like that. Okay, great. So, as you can see in the graph, the function has different tangent lines at different points. You compute the slope of those tangent lines. That gives you the derivative evaluated at those different points. Now, That's the graphical intuition. Now let's do some algebra. Suppose that you have a function, an actual function, and we want to calculate the slope of the function, let's say x squared, at the point a equals 1. I'm going to make a drawing here so you can see it. I know it's supposed to be an algebraic example, but let's do a drawing anyways. This is the point 1. And here's the parabola. The slope of the tangent line is going to be the slope of this line right here. Now what slope do you think that line has, more or less?
2.
More or less 2, right? Awesome. So let's see if you guys are right. So the slope at a equals 1 is equal to the limit, and then we basically apply this formula right here, that says that the slope is the limit when x tends to a of f of x minus f of a divided by x minus a. Now what is a in this case? It's 1. And what is f of x? It's x squared. And what is f of a? Well, it's f of 1, or 1 squared is 1, right? Divided by x minus 1. Okay, you agree? Great. So now we're back to our last couple of lectures. How do we solve that limit? Well, let's go back and remember. We have a quotient. The bottom part goes to 0, right? When x goes to 1. The top part goes to what? Goes to 0 too, right? Remember what we were saying, that it's very unlikely for that to happen, but that's the most interesting case? This is how it works, right? So the top part goes to 0, the bottom part goes to 0, so we have to rephrase. We have to manipulate algebraically so that we can solve the problem. In this case, how do we rephrase?
Factor out x squared minus 1.
Okay, factor out x squared minus 1 into x plus 1 and x minus 1 divided by x minus 1, right? And we're in luck because, as it turns out, we can cancel out the top part and the bottom part. And this is the limit when x goes to 1 of x plus 1. And of course, as x goes to 1, that thing goes to 2. So you were right. Fantastic. Okay, our calculation shows that the slope of that line should be 2, and you can see in the graph that it's more or less true. It's more or less true. It's more or less 2. Okay? Right. So questions? No questions. Okay. Let's do a more complicated example. So, example, we're going to throw a ball up in the air. So, we got a ball. That ball is getting thrown up in the air, and then it falls back down to the floor. You're throwing it up and then down. And the height of the ball at time t is f of t equals 100t minus 16t squared plus 20. Okay, what that means is that presumably somebody is standing at height at some scaffold or something at 20 feet high, and they're throwing the ball at time 0. So at time 0, the height of the ball is 20. It starts going up really fast. Eventually it starts going down again because you see there's a minus 16t squared. Okay, you can ask all kinds of questions about this kind of function. For now, what we're worried about is about the velocity of that function at a particular time. So the question is, calculate the velocity at time t equals 2. Okay, now we talked about this last time, but let me just remind you that the velocity at a time is essentially equal to the slope of the tangent line. Okay, we talked about this in a previous lecture, but let me just remind you again, if you didn't remember, is that the average velocity, if you were at a time, if you can look at the ball, you can measure the height of the ball at any time, and you want to calculate the average velocity from time from time 2 to time t, let's say 2.5. The average velocity will be how much distance you covered, so f of t minus f of 2, divided by how much time it took, which is t minus 2. This is the distance covered. And this is the time that it took for the ball to cover the distance. Right? Average velocity. Now, if we wanted to calculate the instant velocity at that time, we have to calculate the average velocity at smaller and smaller intervals of time. So the instant velocity is the same thing as before, is the limit when t goes to 2 of f of t minus f of 2 divided by t minus 2, which by now has a name, and it is called f prime of 2. It's the slope of the function f at the point 2. Great. So how do we compute that? Well, we use the definition. The definition of derivative, once again, f prime of a is this thing, right? The slope of the function at point A. We're going to plug in the function that's 100 t minus 16 t squared plus 20, and we're going to subtract f of 2. Okay, f of 2 is 100 times 2 minus 16 times 2 squared plus 20, right? So that's, I can write a single parenthesis. I can write in a parenthesis the whole thing, but I'm going to write the whole thing without the parenthesis. So it's going to be minus 100 times 2 plus 16 times 4 minus 20. Is it clear why the signs got flipped? Right? It's not minus 16t anymore. It's not minus 16t squared anymore. Why not?
But you made correct?
Because of the minus sign, right? In principle, I should write a parenthesis, but I got rid of the parenthesis, so I'm flipping the signs of everything. Okay? Divided by t minus 2. All right? So how do we now simplify this thing? We probably need to simplify it a little bit. You see that 20 cancels out with this 20 over here. So that's good. All right, what else? Well, actually, I'm going to group together a couple of things. Okay, I'm going to write this first term together with this term over here, you see they look a lot like each other. It's 100 times t, and this one is 100 times 2. So I'm going to write this as 100 times t minus 2. Okay? Now, I am actually going to break that fraction off, write it on as its own thing, and I'm going to now put together this second term and this term over here together. So this is, hold on, let me see. This is going to be 16 times t squared. No, sorry, 4 minus t squared. Ah. Four minus t squared divided by t minus 2. Okay, so as you can see, I grouped the first one and this term and this term together, and I grouped this term and this term together, and I separated it into two different fractions. Now, what happens with this as t goes to 2? Well, this thing cancels out with this thing over here. So this is the limit of 100. And this thing can be written down as 16 times what? Well, once again, if you calculate what this thing goes towards, when t goes to 2, the bottom goes to 0, the top goes to 0 too. Once again, we're out of luck. It's not easy to compute this. We have to rephrase. Yep. We're going to factor out again as before. 2 minus t, 2 plus t.
You can't do that. You have to take out a negative, don't you?
Yes, you can. You have to. That's right. You're suggesting that we have to take a negative out. I ran out of space, so let me write this on the side. So I can write this down. Okay, so I can cancel out the t minus 2 with the 2 minus t, except that there's going to be a minus 1 showing up. Do you guys agree with me on this, or should I write this more carefully? Okay, so this thing here is minus 1 times t minus 2. And this t minus 2 cancels with that t minus 2, and you have a minus 1. So this is equal to the limit as t goes to 2 of 100 minus 16 times 2 plus t. Okay? And that is equal to the, well, I guess we can already compute it, right? What's the limit of this thing when t goes to 2? It's 100 minus 16 times 4. Okay, that's 64. And 100 minus 64 is 36. So there you go. Now we computed the velocity of a ball at a particular time using limits. Okay, now let me ask you a question. This was all math, but what about the units? What units do we have in this problem? I didn't tell you, right? So let's suppose that we have feet and seconds. Feet for time, feet for distance, and seconds for time. So what is the unit? What are the units for the answer?
Feet per second.
Okay. How do you know?
That's for velocity. Those are the units normally used.
Yes. So basically, when you write the limit when t goes to 2 of f of t minus f of 2 divided by t minus 2, the top part is in feet, right? And the bottom part is in seconds. So the limit is in the units 36 feet per second. Awesome. Do you guys have any questions? No questions? Everything's clear? All right, fantastic. So in general, f prime of A can be thought of as a rate of change. So for example, if the function is in units of feet, then we're talking about how the function is changing, increasing or decreasing over time. How many feet per second is it increasing at a particular time? That's the velocity. But it doesn't have to be velocity. We can talk about rates of change in different contexts. For example, let me give you another example, is that the population of bacteria in a sample is given by P of t at time t. So this is the population of bacteria in a bottle at time t minutes. So can anybody tell me, in the wrong words, what would be P prime of, let's say, 10? What is P prime of 10? Of course, it's the slope of the tangent line, right, of P at the point 10. But how do we interpret it? Okay, population of bacteria at 10 minutes. That would be P of t, right? P of t is the population. But what about P prime of t?
Oh.
Uh-huh. Yes. How much it's? How big it's gotten?
The rate of change.
More, it's closer, yes. Yes, in the back. Yes. Population growth per minute. Okay, that's right. So for example, if P prime of 10 is equal to 1,000, that means that, how would you interpret that information? That means that the bacteria are growing at a rate of 1,000 bacteria per minute, right? So it's the rate of growth of bacteria. It's almost like the velocity of growth, if you will. So if P prime of 10 is 1,000, that means that at that point, there's a growth of around 1,000 bacteria per minute. So then, P prime of t is the rate of growth or decay, right? P prime of t could be negative, of bacteria at that time. And the units are in number of bacteria per minute. Awesome. Let me give you another example. So, suppose that you have a factory and you're producing chairs. Okay? And C of let's say X is the cost of producing X chairs in a factory. So you got your factory, your chair factory going on. You're wondering how many chairs you should produce. And without going very far, we have in a factory, you have fixed costs. You have to pay your employees. You have to pay mortgage on the space that you bought. Those are fixed costs. And then there's going to be materials costs. You know, the more chairs you make, of course, you're going to consume more materials. And your machines have a certain capacity. So after if you want to push it a little harder, maybe you can produce more chairs, but it's going to get more and more expensive. Sometimes you cannot get the materials at the right time, or you can only get a limited supply, and you would have to pay a premium for additional materials. So the bottom line is that depending on how many chairs you make, it's going to cost you a different amount. Now, as a merchant, you want to know what's the optimum number of chairs you should produce. Okay, so as part of that information, you want to find out that function, C of x. And afterwards, we're going to optimize that more. But let's for now just think about C of x, and let's think about the derivative, C prime of x, and what it means. So let's see. C of x is in dollars, right? So C prime of x has units of dollars per chair. So nothing to do with what we were saying before. X is now measured in number of chairs. Okay? So C prime of x is in dollars per chair. What does it mean? So for example, if C of 1,000 is equal to, let's say, $50 per chair, that means what?
If you get 1,000, costs you $50.
Say that again?
That if you get 1,000 chairs, each one will cost you $50.
It's at the 1,000 chairs, at that particular time, you produce one chair per will cost $50.
Okay, so if I understand you correctly, you said if you're producing 1,000 chairs, the cost of each chair is $50. Okay. Now, what does that mean exactly? Does that mean that the cost of those 1,000 chairs is $50,000? What do you think? Does it mean that is this the same as saying that if I construct 1,000 chairs, it's going to cost me $50,000?
No.
Yes.
No. Because this 1,000 is means at the 1,000 only one point. Not it's not linear. So.
That's right. If you remember, forget about chairs for the moment, and think about what the mathematics says. The mathematics says that C prime of 1,000 is the slope of a function at the point 1,000. It has nothing to do with the value of the function anywhere else. It's just talking about the local tangent at that point. So it says nothing about how much the other chairs cost. Maybe they were very cheap. Maybe they were more expensive. The point is not that it cost me $50,000 to produce those 1,000 chairs. I'm just trying to confuse you here. I'm just trying to make sure that you understand the concept right. The point is that if I am making 1,000 chairs, at that level of production, it's going to cost me $50 per chair to produce more chairs. Right? So more or less, if I wanted to produce 1,001 chairs, it would cost me $50 more than it would cost me to produce 1,000 chairs. If I wanted to produce 10 chairs more, in other words, if I wanted to produce 1,010 chairs, it would cost me about $500 more than if I produced 1,000 chairs. Does that make sense? So it's the additional cost per chair that it would cost me at that level of production. Oh crap! I'm sorry. I really should have written C prime. This is C prime, sorry. So, so C prime of 1,000 is the rate of cost. People don't really talk about it in this way, but rate of cost to produce additional chairs at this level of production. For instance, one additional chair would cost about $50 more than
Then 1,000 shares.
Then 1,000 shares, yeah, right. So one additional chair means if you produce 1,001 chairs, it would cost you $50 more than producing the 1,000 chairs. In economics, this is called the marginal cost. Okay, great. Do you have any questions?